today, Mihnea is the director of engineering for the languages and relational technology team. I mean, and just remember, it's just been a short while ago when he joined us right at the school, and it's been a fun experience working on a lot of things with him. But anyways, let's stick to the topic here, right? So Mihnea, maybe you can talk about when you started working on the YSQL API and how it happened and any of the details.
Yeah. So maybe I can give the broad context first. That initially, when we started on our SQL API, we actually explored re-implementing the Postgres API kind of natively in C++ to extend our database. And we tried that actually for a while, for several months, and we slowly realized that that's not a very tractable thing to do. And then we started this idea of, can we reuse Postgres and at least the upper half of Postgres, and then replace the storage layer with our distributed storage engine, which is DocDB. And that's when I started to kind of work in that area more. I think that was around July or mid-year 2018. And that was a lot of really fun work. I think our first kind of beta release and our first kind of functional version of it was around PostgresConf in, I think, around October 2018. At that point, we just had create table working, and reads and writes, joins and some other stuff were working, but I don't think we had secondary indexes. We didn't have foreign keys. And I think all our DDLs were basically single node. We had to go to one specific node to kind of execute DDLs. And I think January of next year, 2019, it was when we had our fully A-chain scalable version. And then as we built more features and tested it, I think our first GA release was August 2019 as part of Yugabyte 2.0. So that's kind of the start of the journey in YSQL.
That's awesome. Yeah, I remember some of these, right? Like in 2018, I think around October, that was the PGConf Silicon Valley, right? The first PG Silicon Valley, and it was a fun time. It was really awesome. Okay, so you said that we started out rewriting it, and then we switched to reusing or exploring reusing and figuring out, right? So can you talk about some of the goals behind the Postgres support and compatibility that we wanted to achieve in YugabyteDB that made it necessary to switch? And if I remember, it was about 6 months of actually trying to write it, and then we said, you know what, all the 6 months of effort, but it's not the right option. Let's change options midway, right? It's always a difficult decision to do that. So what made us switch? Can you talk about that?
Yeah, so I actually have some slides about that. So let me see if that works. I'm gonna share my screen, and hopefully this works and folks can see.
Yep.
Yeah, the first interesting part is just the breadth of PostgreSQL in terms of the set of features. So these are just some selected features, is by no means everything, but there's stored procedures and functions, and each of those have like different languages. There's SQL, there's the procedural language PGSQL, and then there's C functions and so on. Then there's user-defined types, which again, there's different types. There's various kinds of triggers, indexes. Obviously, there's a whole extension framework, which is also quite interesting. Then there's authentication authorization from LDAP to column and row level security, foreign data wrapper. So just the breadth of features is really huge. But then one of the initial motivator was something very simple, and I wanna show that example, which is just something that you do kind of the first time you use Postgres, or also when you use Yugabyte, you might want to just list the tables or list the relations that are in your current table. If you do that in PSQL, it sort of just works. But if you look underneath of what's happening, is the PSQL generates a query that looks like this. In fact, it's literally this. And if you look at this query, you see that it uses case statements, it uses joins, it uses stored procedures for formatting and for comparing certain things, order by, and all sorts of things. So just getting the very basic list tables to work requires quite a bit of SQL coverage just to get that first step. And obviously it can only goes harder from there. So that was actually, this query literally was one of the motivators for kind of exploring, hey, can we actually reuse this to get the level of compatibility that we really wanted from Postgres? And I think you'll see later that I think we got pretty close to where we wanted.
That's awesome. Yeah, I remember this defining query, although it's just a simple query, right? It's just the query that lists tables. So fortunately, it was one of the easy ones to get started that told us that's not the way to go, or not quite. Right?
Yeah.
So, okay. So in order to get here, can you explain how things work, like how YSQL API achieves Postgres compatibility, what happens underneath the hood, and can you just like talk about a little bit of, like creating tables and, inserting and selecting data?
Yeah. So I'm going to give a very high level overview because it's obviously quite complex, but hopefully it gives folks a flavor of how it works. So let's start with looking at Postgres and kind of unpacking it a little bit. And, I have an SQL app and you have all the Postgres components, which is a little bit simplified here, but you go to Postmaster, and if it's a query, you go to the rewriter for views and planner, optimizer, executor, and then eventually you go to write to disk. So that's kind of how vanilla single node Postgres installation works. So now what we wanted to do as a goal is to reuse as much of we can of the Postgres upper layer, but then change the storage layer to Yugabyte. Now, in a more concrete way, we can't just reuse the upper layer because we need to change a bunch of things. We need to change where we send the data, but also more subtly, we need to change the execution, the planner. Now we need to take into account network costs, RPCs, and so on. So there are changes to be made in kind of different areas that we've made. But fundamentally, a lot of the upper layer is actually reused or just extended with kind of new ways of doing things. So that's the architecture on the kind of single node level. And then if we zoom out to an actual cluster, so here we have three Yugabyte nodes. So on each of the nodes, we basically have DocDB, which is our storage layer, running alongside what is now effectively a stateless Postgres, because the state of Postgres is now stored in DocDB. Now an SQL app can connect to every node, and each of these status Postgres will be able to talk to each DocDB node it needs to aggregate, to get the results, aggregate them, and get the final result to the user. And that also means that you can tolerate failures of the nodes. So at the storage level, if a DocDB instance dies, then tablets will get rebalanced across the live nodes. So you can still make progress and do work as long as you still have the required quorum. And then at the Postgres layer, because it's stateless, everybody else can still talk. Obviously, you cannot talk to this instance anymore, but you can connect always to any live node. So an application that's connected to the whole cluster can continue and working even under node failures. So that's the high-level architecture. And then to go into kind of DDLs and how to describe relations, I'm going to use another simple example and look at tables. So the high-level idea is that for each Postgres or YSQL table, there is an internal DocDB table, and same for index. And then we have these special tables for system tables like PG class and PG attribute and so on that store the metadata of Postgres. And all of those metadata tables share a single tablet, which we call the system catalog tablet. And then in DocDB, regardless of them, they're stored in this kind of key to document format that DocDB uses. So let's go through an example. And yeah, this is the system catalog leader. So here we have the system catalog, and we have the replicas for the system catalog. So here, everything related to PG underscore tables, PG class, PG attribute, and so on will be stored in this tablet. So for example, if you go to create table, let's say we receive that request, we would go first to the leader to record the schema change. So in practice, that would mean inserting to PG class, insert a bunch of rows into PG attribute, and the other tables that are needed for that. And then that change gets replicated. And at this point, we know there is a table, but of course, that's not enough. We have to create the equivalent of the files, the storage layer. So then we create tablets where to store the data. So in this example, we assume the table is pre-sharded into 3 tablets, T1, T2, and T3. And then DocDB would automatically split those tablets so that we get and they're like leaders. So in this case, we have the first node is the leader for T1, and then has for the other two, and so on. So after this, the table is basically created. So that's how create table works. And then for non-tables, you don't have to create tables. Like for a view and so on, you just have to store it in the metadata. For the write path, it's somewhat similar. Like for inserts, we just write to those tablets that we have created. For updates and deletes, it's a bit more complicated with push downs, but we'll leave that for later. And then we do, DocDB has its own transaction layer for distributed transactions. So whenever we need to do transactions, either explicit transactions or implicitly for indexes, we use the DocDB transaction layer. So again, let's look at an insert row. Again, we have to find the tablet reader, and it can be on the same node or on a different node. We send it to the right node, and then we wait for Raft to replicate the changes, and then acknowledge back to the client, and basically we're done. The read path, it's a little more complicated because there's a lot of cases here. I'm just going to pick some simple selects. Generally, an execution plan involves sending one or more scan requests to various DocDB tablets. It can be just one if everything matches, or it can be more. Then DocDB may do some additional filtering or optimize the scan to just a particular range, and then later on sends it to the original node where it can do any additional work. Here are some examples of some scans that you can push down. Just going to an example, so let's say client sends a select statement, Postgres or MySQL analyzes the query, figures out how to execute it, including which tablets it affects. In here, let's say it affects all the tablets, so it fetch a row from T1, pre-filter by DocDB to the extent that it can, same for T2, same for T3. Then if there's any further filtering that DocDB cannot do, Postgres will do that and respond to the client. So that's the high level of how each of the steps work. And I'm sure Karthik will have more questions about that, but that's the high level.
Yeah, no, that makes total sense. Now, one of the higher level things, right? Like, is that like we talked about, obviously, as you said, a very high level simplistic view, right? Like, what happens if there are more complicated queries and you have to, like in this diagram, it looks like all of the queries and the data are moved to the node processing the query, and there's really distributed processing, right? But and I know that's just because you just picked simple examples, but can you just touch on?
Yeah, so one of the things we worry a lot in, obviously because it's a distributed system, is where we do the compute, and ideally we minimize the shuffling of data across the nodes, and we do as much of the compute and filtering in this case closer to the data. So that means that for selects, we try to push down conditions to the DocDB layer. So we send as few nodes, and so that means we push down expressions, which is actually kind of some work in progress to extend that, aggregates, like count star and so on. You can just count locally and then aggregate the results. But it doesn't just apply to reads. One example is for updates, where the kind of standard way to execute it, where you have a where clause is, and that's what Postgres does typically, is you just read the rows, you get the rows back, you filter and you do whatever you need to do, and then you have another request to delete the rows kind of one by one. And of course, we try to not do that and do one RPC where we both read and delete the rows locally on that tablet whenever we can, so that we minimize the RPCs. So there's a lot of work that we have done and we are continuously doing in the execution layer and also in the planning layer, so we can execute this optimally.
Makes sense. Yeah, makes sense. So this begs another question, right? So if you zoom out a level, can you describe, like, this is the architecture, right? But now let's talk about the code, right? Obviously, the starting point was, the Postgres code base on one side and the distributed storage layer of YugabyteDB, the DocDB on the other side, right? So can you describe which parts of Postgres code that, needed to be changed? Like, for example, like, did we change the native flow? Did we change the foreign data wrapper flow? Or how did we handle initDB? Like just how is this is a high level? Right? There's too much to go into.
Yeah, that's a great question. So initially, we actually started with foreign data wrappers way back in those early 2018 days, because it was the simplest API to extend. But by now, we are much more tightly integrated. So we've declared basically our own storage module, basically our kind of Yugabyte access method that we use for index scans and also for for writes in a similar path. So up to quite low in the Postgres execution model, we have our own plugins and hooks in the various places, but it kind of follows the standard path that a regular write in Postgres would use, up to quite low until you get to the storage layer, where of course it has to go to YugabyteDB. So now for index scans and for writes and so on, we kind of use something very close to the Postgres path, except in our module. But we did start with foreign data wrappers. And regarding InnyDB, I think that's also a great question, because that was one of our first tests for the database, because Postgres starts the database, or as part of initializing, it already creates a lot of stuff. And I actually have a shell here that maybe I can just show. So if we just look at the list of tables in basically an empty database that I just created, you already have 313 relations, or around 300 relations, and some of them are indexes and views and other stuff, but there's a lot of tables that start from scratch, and each of those tables have a lot of data to begin with, like this is the table of procedures or functions.
So I guess what this shows is that it's not just the Postgres compatibility at the query or the creation level, it's also the information schema, right? Like the system cat is also compatible.
Exactly. Yeah. So we use exactly that. And when you install Yugabyte, you get this version of InnyDB that's compatible with the Postgres version that we're compatible, that already has all the data.
So maybe that gets to the next question, which is what version of Postgres are we compatible? And a very often asked question, which is when and how are we moving to the newer versions?
Oh yeah, that's a good question. And it's also a timely question, because that's something we're kind of very actively working on. So we actually started with Postgres 10.4 all the way in around July 2018. And then we upgraded to Postgres 11.2. So we've been on that version for a while, and I can show that as well. So this is our version. So we append the YB version here, but it's basically Postgres 11.2. But now we are sort of actively in the middle of upgrading to the latest version of Postgres 13. So that's Postgres 13.5, I believe, which came out in November.
Excellent. So, okay, so now that you're on the shell already, right? Like, can you talk about some of the more novel or advanced Postgres features, and maybe show how some of these work?
Yeah, definitely. So that's where I think the compatibility aspect comes in, because we support a lot of things based on kind of our design and our approach. So we wanted to show a couple of things that that I think are personally cool. So one is extensions, and as part of extensions, I'm also going to kind of demo user-defined times user-defined functions. So let's start with something like PG crypto. So I'm just going to run this command to encrypt a password. I don't have the PG crypto extension created already, so this is expected to fail because this function doesn't exist. So now I'm just going to create the extension PG crypto, which is bundled with Yugabyte, so you can just run create. And now if I do this now, part of what this extension does is that it defines this function, which is implemented in C. So it's that kind of function. We support the other ones as well. So now you can do various things, and it supports other things. I think a popular thing of PG crypto is the random UID generation. So that's a really cool thing, and we support actually quite a broad set of extensions. One that we have enabled by default is PG stat statements, which allow you to do quite this is a simplified query because there's no time to show everything, but basically you see the queries that I've run around here. So it gives you the total time, the number of calls, the rows affected, and a bunch of other stats, mean, max, variance, and so on. So that's something that's actually enabled by default. And another extension that I like, let me clean this up a bit, is, and I don't know how to pronounce this, but I pronounce it RIFC, but it's an extension, it's a pretty big one, that reimplements as user-defined types and functions a lot of standard Oracle utilities, so you can more easily migrate from Oracle to Postgres, or in this case, Yugabyte. So let me just create that extension. So once this extension is there, we can do things like use a Oracle function, like in this case, sysdate. It's a very simple one, but it's an Oracle function, and one that I think would be a favorite for people who come from Oracle. You can now do this. Yeah, you can do this, which obviously is not necessary in Postgres, but for compatibility, that's also added. So it's a pretty big extension, has a ton of stuff, and that's again an extension that you can just use in Yugabyte. So I think that ecosystem of extension together with user-defined types, stored procedures, and all of that is really powerful, and there is actually too many to show here. Another example I want to show, which is very recent, kind of fresh off the press, is GIN indexes and text search. So I wanted to show an example here. So I already have this table, so let me just show the schema. So this is just a very simple table, which has an ID and a message, which is now directly encoded as TS vector, but you can think of it as a text encoded as the way Postgres likes to do text search. And then there is a GIN index. It says YB GIN here because it's our version of GIN index, but think just GIN on message, which allows us to kind of search that efficiently. And now, just for a demo, just inserting a couple of rows. So here I'm inserting one row. The key components here is this is the text. And here, when I'm creating the TS vector, I'm specifying the language. And now the TS vector knows what to do with this word. So
stemming that portion, right? Like the language.
Yeah, exactly. Exactly. So I'm going to insert a couple of things. I see I'm not the most creative examples here, but I think functionally they have. So these are the sentences, but if you search what's ended up in the TS vector, you see that the words were normalized, the kind of connective words were removed, and now you just have cat, dog, and rain. So there, all of that is being done. And so on for the others. So, and now you can do a query like think of this as contains, if you're not familiar with GIN indexes on text search, but this is basically search all the messages that contain dog. And here you get, the first and third line here contain dog. And obviously this query will work regardless, even without the index, but just showing here for the explain that we do actually use the index on messages. So if you actually had a lot of data, it would be efficient as well.
Got it. Awesome. Awesome. So got it. One thing I see is it says the rows is 1,000, right? Like what's that about?
Oh yeah. So it's because it's sort of intentionally, I didn't want to run analyze on this. So let me do that now. So if I run analyze now, it will know the number of messages. But if I run explain again, then it's being too clever and it will know, okay, there are 3 rows, but that means it's not really worth it to use the index for 3 rows. So then it will just do a sequential scan with a filter. So it's not as nice for the demo. So that's why it kind of shows the default value.
Got it. Got it. Awesome. So there's a question, one of the user questions, which is, does the engine support auto-incremented IDs for primary keys? And how is it implemented? Maybe we'll just talk about if it is supported, and we can take the how is it implemented offline.
Yeah, so we support sequences and auto-incremented IDs, but generally that tends to be a bit of an anti-pattern in a distributed scenario, because we don't want a bottleneck or a kind of central place that gives you the auto-increment IDs. Now, Postgres and Yugabyte supports the cache value for sequences, so which allows you to kind of pick up more at a time, which kind of mitigates the performance issues. So that's kind of what we recommend. So we support them, and in terms of performance, there's this cache value for sequences that you can play around with to optimize the performance.
Assign the IDs in batches to each machine.
Yeah,
so,
exactly.
Awesome. Okay, so let's keep going. A couple more questions before we run out of time. So what are some of the Postgres features that we do not support?
Yeah, there's still a few. Even though we have really good coverage, there's a few. And some of them are things that, because of our architecture, it doesn't really make sense. So for example, because we don't use the transaction layer of Postgres, use DocDB, we don't use the storage layer of Postgres, we use DocDB. Some things like shared buffers, the Postgres style table spaces where you can put the location on disk on things, they don't really make sense to us. There's also other things like listen notify where we kind of do it differently. But there's also some big features that are still in the roadmap. I think 2 big ones are pessimistic locking when it comes to kind of Postgres compatible transaction semantics. Maybe I want to also call out that recently it's still a beta feature, but we've landed support for read committed isolation. So we now support serializable, repeatable read with snapshot isolation. And now folks can also try out read committed isolation, but pessimistic locking is kind of the next thing after that. And another big one is gist indexes, which PostGIS is a very popular extension that makes use of that. So those are two big ones.
Awesome. Awesome. Great. Okay. So here's another one that comes up often, right? Like, so, or something that people talk about often. So Postgres has some weaknesses. It's an awesome database, but every database has its weaknesses, and so does Postgres. So there's things like connection overhead and transaction ID wraparound and some of these type of things, right? Which of these are inherited by YugabyteDB, and which of these are not? And are there plans to fix any, and so on? Like, what's the general thinking there?
Yeah, so high level things that tend to have to do with the storage layer, we tend to not inherit. And things that have to do with the upper layer of Postgres, we tend to inherit, and then we work on improving them. So one of them is at the high level is how Postgres deals with connections, and each connection is a process, and then they have their own cache, and then there's a little bit of overhead for the connections, and there's a limit for the connections. So we inherit that. We've made some improvements on our side, and obviously being a multi-node database, it also helps that you can have more connections across more nodes. But that's one of the designs that we've inherited. And again, for compatibility, it's something we haven't changed. We just optimized how it works internally for us. But there's others that actually don't affect us. So, for example, transaction ID wraparound is a common or a somewhat common issue in Postgres. We don't use the transaction layer. Our IDs are kind of larger than the Postgres one, so we don't have that issue. Also, vacuuming, that's a very common common thing in Postgres. So we don't do vacuuming, we do compactions, but the way we store the data, because we don't do as many tuple rewrites, for updates, we just update the individual rows, and we don't have to rewrite the tuple. We don't get the equivalent of what would be in Postgres, get a new CTID, and then you have to rewrite a bunch of stuff. So that means both that we can be more conservative with updating indexes. We can avoid updating indexes if they're not really modified by a query. And also it means that when we end up doing our compactions, we usually have to do less work than Postgres would have to do.
Awesome. Fantastic. I think that brings us to time, but there's a couple of more interesting questions, but I think you folks would just have to join our Slack channel, YFTT, to ask Mihnea those. Like, for example, what were some of the unexpected or challenging things that came up, and so on. The other thing that comes up is, why did we not contribute this back to PostgreSQL itself, right? And it just has to do with the invasive nature of the changes. And we tried, right? But it's just difficult for a project to focus on two things, right? Is it going to be a single node database or a distributed database? And YugabyteDB itself is fully open source under the Apache 2.0 license. So if you folks have more questions, feel free to join our Slack channel, yugabyte.com/Slack, and the YFTT channel. We're happy to talk to you folks there. Anyways, join us next week, same place, same time, to talk where Kannan and Bogdan are going to be talking about sharding strategies in YugabyteDB, and what really makes it automatically scale and shard and so on and so forth. All right, until next week, see you guys.